So what I try to do today is to give you an overview of the A-ParaDDisE project, which is based on a previous project, as you will see. And we're very much upstream of the drug discovery, of the pipeline of drug production. So we're in the discovery phase as well. The A-ParaDDisE project is an EC-funded FP7 health project with 17 partners in Europe, Brazil, and Australia. We're focusing on the neglected diseases, schistosomiasis, leishmaniasis, Chagas disease, and as well malaria, which is not strictly a neglected disease. And we're using basically a target-based approach, although not entirely. And we're interested, unlike the previous speakers, in enzymes that are involved in epigenetic modifications of the chromatin. The ones we're interested in are those that acetylate or deacetylate or methylate or demethylate the histone tails, which you can see on this diagram. Now these form part of the histone code, where there are a number of other types of modifications, which are involved in controlling transcription. And the enzymes that affect these modifications, the histone-modifying enzymes, are drug targets in a number of pathologies, especially cancer. There are a large number of histone deacetylase inhibitors which are in clinical trials, and 2 have been approved. The challenge that we have for these enzymes is that they are conserved and they perform conserved functions. There are 2 main challenges. One, that individual HMEs would be valid therapeutic targets in these parasites. And the second, that structural differences at the catalytic sites of these enzymes will allow us to develop selective inhibitors compared to the human orthologs. And so target selection is crucial. And there are different ways in which we carry out target selection based on different criteria. One of the main ones is obviously gene or transcript knockdown in the different parasites. We also use phenotypic assays with HME class inhibitors and bioinformatics and modeling as well to inform these choices. What I'm going to do now is to show you some results we got in a previous project. The A-ParaDDisE project started in February this year. Our previous project was called SetTrend, which focused only on schistosomes, and was funded from 2010 to the end of 2012. And so I'll give you an illustration of the approach we intend to use, in which we are continuing for the schistosome targets in the A-ParaDDisE project. The example I'm going to take is a histone deacetylase, which is a class 1 histone deacetylase, histone deacetylase 8, which interested us from the outset. These just rather subjective views. It was highly expressed at all life cycle stages. The HDAC8 is not normally highly expressed in mammalian cells, only in cancer cells. And it was phylogenetically distant from the human ortholog and had different structural differences in the active site and outside it. So this looked to be an interesting target. And so we did what we could do in schistosomes to look at transcript knockdown. We can't actually do gene knockdowns in schistosomes, not targeted gene knockdowns in schistosomes for the moment. So we can use RNAi. And RNAi on the larval stage is schistosomular. But we have to re-inject these back into mice after treatment and then assess worm and egg burdens 45 days after this reinfection. So this was done for histone deacetylase 8. As you can see, there is a significant reduction in worm burdens, and this was true especially for egg burdens as well. After this treatment compared to the controls. There are a couple of other potential targets shown on this. Now, I should point out that RNAi is very hit or miss in schistosomes, and you can get a 0 knockdown of transcripts or very good knockdown or anything in between. So it's not applicable to all targets, and we had some disappointments. Another problem is the half-life of some of these proteins, which can be long. We did this again in adult worms. Sorry, I should say the previous work was done in a partner laboratory in Brazil, in Guilherme Oliveira's lab in Belo Horizonte. And this was done in our lab, and it's RNAi in adult worms. And this, again, when you do this, you knock down the transcript, you can produce differences in the testes, and particularly in the ovary, shown on the right of female worms, where the ovary becomes much smaller and shows some morphological changes. So taken together, we felt that these were indicative that SM-HDAC8 was a reasonable target. And so this is the target we went forward with in the CETRAN project initially. And you've already seen from the previous speaker, a bottleneck can be protein production. We were lucky with this one. We've been less lucky than them for other proteins, I have to say. 19 out of 23 is very good for schistosomes. But SM-HDAC8 was produced, and this was done in the IGBMC in their pipeline, which is very similar to the one you've just seen. And it was produced in sufficient quantities, mainly by Martin Marek, to enable us to do both high-throughput screening and target-based screening based on structural studies. I won't talk about the high-throughput screening today. I don't really have time. So I'll just go through the structural studies we managed to do. And this, again, was done by Christoph Romeo and Martin Marek in Strasbourg. And the crystal structure of the APO enzyme was solved to 1.8 angstroms. And as you can see, comparing the top two diagrams which correspond to the schistosome enzyme compared to the human enzyme below, these structures look very similar. And if you superimpose them, you can see they are very similar. The only differences are these loops which you can see on the outside of the molecule, which correspond to these insertions within the catalytic site, but which are on the outside of the molecule, which don't affect the catalytic site itself, and may form the basis of structures for protein-protein interactions. We don't know that yet. But looking more closely at the catalytic pocket, there were differences. One was the histone 292, you can see on the above right in the schistosome enzyme compared to the methionine 274 in the human enzyme, which introduces a charge difference in the pocket. And more strikingly is the conformation of the phenylalanine 151 residue, which is flipped out of the pocket, you can see, in the schistosome enzyme. And this is due to the substitutions of residues around the catalytic pocket, which allow this flipped out configuration. The phenylalanine 152, which is the equivalent residue in the human enzyme, is blocked in a flipped in configuration. Now this leads to a difference in pocket architecture, which we think we can exploit. This, you can see it leads to a slightly broader and shallower pocket. This is clearer from a side view. So we think that this should allow us to design compounds which are bulky and have perhaps a higher content of hydrophilic groups to exploit the charge difference as well in order to get selectivity. As I said, I won't go into the high throughput screening, which has produced some interesting compounds which we're pursuing. The in silico screen was done, as you can see on the left, and with using a certain number of screens and then docking into the active site using the crystal structure. And a number of these which seemed likely to be potent were tested for inhibition, and we retained compounds active in the nanomolar to very low micromolar range. On the right, you can see a couple of examples, so J1038, J1075. Now, these are, I should say at the outset, these are not compounds that we're pursuing. These are just to illustrate how we think this works. So compared to the pan-HDAC inhibitors, SAHA and M344, which you can see above, these two inhibitors show better selectivity for HDAC8 over other classes of histone deacetylases, the class 1s, HDAC1 and 3, and class 2, HDAC6. But they're not yet selective for the schistosome HDAC8 over the human HDAC8. We have other series which we're working on and which I'm not allowed to show you today. But J1075 shows you how this can move forward. This was crystallized again with the HDAC8, schistosome HDAC8. And as you can see, it exploits the wider catalytic pocket of the schistosome enzyme, and, but not the difference in charge. J1075 was tested against schistosomes. We tested it against larvae in culture, and it causes dose and time-dependent death of schistosomia, the panel on the right. And this is seemingly due to induction of apoptosis, shown by tunnel staining on the left. And we did some very preliminary in vivo studies using a single dose of this compound in infected mice, and it does produce a significant reduction in worm and egg burden. But this is not a compound or a series that we're moving forward with. To summarize where we were at the end of the set trend project, we showed that we were able to pursue this target-based strategy, and we have series of compounds which have novel scaffolds and warheads from both high throughput and in silico screening, novel for HDAC inhibitors that are effective in the nanomolar range. We have some lead series which have been evaluated, and we're moving forward on these with bioguided optimization to improve both selectivity and bioavailability. We've also carried out high-throughput screening on another target, which is a sirtuin-2, which is another deacetylase, but of a completely different family. And inhibitor optimization is going forward with that as well. And there are other targets in the pipeline. So we thought, we felt that this was a viable approach for developing drugs against schistosomes and other parasites. So this led us to the A-ParaDDisE project itself, which expanded on this strategy and extended it to these other parasites, Trypanosoma cruzi, Leishmania, and Plasmodium. And in this approach, we've expanded a phenotypic screening approach in addition to the target-based screening. But I should say that these are phenotypic screening using HME inhibitor libraries and not random compound libraries. Now, the objective is to pursue this same strategy using bioguided optimization. We're including, this time, basic PK and toxicology studies to inform in vivo studies, and we hope that this will allow us to produce a certain number of leads that can then go forward. This will be the challenge, to go forward from this very basic preclinical phase to clinical trials, obviously. I think that's all I really want to say today. I should point out that this A-ParaDDisE project is one of 4 EC-funded projects in this same call, one of which is represented here today. There's a poster I saw for the Kindred project. So there are other approaches ongoing, funded by the EC. I'll leave you with all our partners, and I'd just like to contrast an EC project to what you saw from Dundee, where everything was in-house and on the same place. This is obviously split about with people in Brazil, in different countries in Europe. And so one of the challenges is to keep this effort together once we've finished. We were able to do that with the SetTrend project. All the partners of the SetTrend project are part of this new project. But what happens after this project, the disadvantage is that we only have 3 years, and after that we have to have, if we produce something, then I think we can continue. But anyway, thank you very much.